Alright, so let's look at another example. The instructions are the same. We want to use the first derivative to find the intervals of increasing and decreasing, and we want to use the first derivative test to locate any local extrema. And so the first thing we'll do is take the first derivative. So we're going to use the product rule. We're going to have first times derivative of the second, which is going to be negative e to the negative x, plus second times derivative of the first, which would just be e to the negative x. If I factor out an e to the negative x, I'll have negative x plus 1. Now I want to find out where this function is either undefined or where this function is equal to 0, the first derivative function. If it helps to write this as, say, 1 minus x over e to the x, that you can do that. This is our first derivative. I know that I'm going to get a critical value when the numerator is equal to 0, so 1 minus x equals 0, so x equals 1. I also can get a critical value where the function is undefined, so I set the denominator to 0, but an exponential function of this type never equals 0, so we don't get a critical value from that. So now we'll draw our test chart. We'll put 1 in the middle. There's our critical value. Choose a test value to the left and a test value to the right, and I'll plug into my first derivative, which is right here. When I plug in 0, I get a positive. I'm just going to get 1 in the numerator, and e to the 0 is also 1. When I plug in 2, I'm going to get negative 1 in the numerator and e squared in the denominator, so this will be negative. So using the sign chart for f prime, the function is increasing from negative infinity to 1, and it's decreasing from 1 to infinity. We have a sign change at 1. Since we're going from increasing to decreasing, we're going to have a local max. We're going to have a local max of, well, I don't know the value yet, but I know it's going to occur at x equals 1. I can use my calculator to, and even if I didn't have a calculator, I could plug 1 in to the original function, and I would get 1 times e to the negative 1. So that would be 1 over, just 1 over e. But let's use a calculator to get a decimal value, and also to look and see, to confirm our analytical work using the graph. So I've typed in my function into the y equals. I started with a zoom 6, but it didn't give me a very good window. I mean, I know my critical value, and I only have 1, it occurs at x equals 1, and so you can play around with the window manually, or you can just zoom in and hit enter. We get a better visual here. And so if I trace on 1, you can see where our local max occurs, and so the local max is approximately 0.368. We could have found that value again manually by finding f of 1. F of 1 would be 1 times e to the negative 1, or just 1 over e. And if we just double check that, if I take 1, let's quit out of the graphing for a minute. If I take 1 and divide it by e, I get approximately 0.368. Alright, so I'd like you to pause the video and try the next 2 problems. The second one, the derivative is a little tricky, but you can handle it. And then start the video again to check your work. And I can't stress enough how just watching me do these is not going to help you. It's really important that you try the problem and then watch the video, so that when you come into class you really are able to ask questions. You can clarify any issues you have once you've tried these problems. So the first one is a polynomial, and so we're going to find the first derivative. F prime of x equals 2x minus 4. Since it's a polynomial, I only have to set it equal to 0. I don't have to find out where the first derivative is undefined, because polynomials are nice smooth curves and their derivatives are defined everywhere. When I solve this, I get x is equal to 2. So I will set up my sign chart. Number 2 is in the domain, so it is a critical value. I want to stress the fact that you should always be checking that these critical values are in your domain. If it's not in the domain, you can have a local max or a local min there. Test point to the left will be 0. Test point to the right, 3. When I enter 0 in for, or substitute 0 in for x, I get a negative. When I substitute 3 in for x, I get a positive. So I know the function is decreasing and then it's increasing. So I'm decreasing from negative infinity to 2 and increasing from 2 to infinity. I have a sign change at a critical value, so that tells me that I have a local min because the sign change went from negative to positive. So we have a local min of, and we'll fill in that value in a minute, but that local min occurs at x equals 2. So we can plug 2 in. To find this local min, we can graph it, or we can just find f of 2. And f of 2, this is where I go back to the original function because I'm looking for a function value here, is 2 squared minus 4 times 2 plus 3. So I get 4 minus 8, which is negative 4, plus 1, so I get negative 1. So I have a local minimum value of negative 1 that occurs at x equals 2. Let's graph the function. Okay. And I'll do a zoom 6. We'll do a standard window to start with. And really all we have here is a parabola. So this is one case where I actually don't even need calculus, but let's confirm our calculus. We said we had a local minimum at x equals 2, so I'll trace on 2 and hit enter, and that local min actually is negative 1, which we've already done analytically. We are decreasing from negative infinity to 2 and from 2 to infinity. Now the reason why we don't need calculus for parabola is because we already have the vertex formula, and I'm not sure if you guys remember the vertex formula, but the x-coordinate of a vertex is equal to negative b over 2a, and the y-coordinate is f of negative b over 2a. And so if we take the opposite of b, which is 4, 2a is 2, so we get the x-coordinate, which is 2, which we just found, and when you find f of 2, we got negative 1. So the vertex is 2, negative 1. So for a parabola or a quadratic equation, a quadratic function, you don't need calculus. We just use calculus to confirm what we already know. All right, and let's look at the last problem. You can use the product rule, the quotient rule here, or you could break it into 2. In this case, it might even be easier to use a quotient rule, so I'm going to go ahead and do that. I've got f prime of x equals bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. I'm going to get 4x to the 5th minus 2x to the 5th minus 2x all over x to the 4th, or 2x to the 5th minus 2x over x to the 4th. One last simplification here. I can factor out an x and cancel it. I can factor out 2x. The x will cancel, and I'll get 2x to the 4th minus 1, that whole thing over x cubed. And so I know I have critical values where my numerator is equal to 0 and where my denominator is equal to 0. So to find my critical values, I'm going to set x to the 4th minus 1 equals 0. That's x squared plus 1 times x squared minus 1. You get no values from that, and the x squared minus 1 gives you x equals plus or minus 1. When you set x cubed equal to 0, you get x equals 0. We have an issue with this because x equals 0 is not in the domain, so it's not a critical value. However, we do need to use it in our tests. So I'm going to test -1, 1, and I am going to test 0 even though it's not a critical value. So this is a critical value, this is a critical value. What I actually have at x equals 0 is a vertical asymptote, so it might be helpful just to put that in so you can see. Because a function, in a function, between any two x-intercepts or vertical asymptotes, your function is either completely above the x-axis or below. So it's important to use that when you're testing, although it can't be a critical value, so you won't have a local max or local min because there is no function value there. So testing, test -0.5, test 0.5. Also we need to the left of -1, we'll pick a test value of -2. And also to the right of 1, we'll pick a test value of 2. So I got 4 test values. When I plug these values into the first derivative, I get negative values in this first interval. I get positive from -1 to 0. I get negative from 0 to 1. And then I get positive from 1 to infinity. So I know I have a local min at x equals -1. I don't have anything at x equals 0, that is a vertical asymptote. I have a local min again at x equals 1. I know the function is decreasing from -infinity to -1, from 0 to 1. I know the function is increasing from -1 to 0 and from 1 to infinity. And so let's check these values on our calculator. I'm going to put this function in y equals. So I graphed the function initially with the zoom 6, a standard window, and the window wasn't that great. So I went in and I played around a little bit, and I changed my x min to -5 and my max to 5, and then my y min I made 0 and my max I made 10. It just gave me a better picture that I could see. So I'm going to graph that. So we can see we've got our 2 local mins. Those also happen to be absolute mins for this function, but right now we're just looking for local mins. And if I trace on -1, I can get the actual value of that min, and that the actual value of the min is 2. If I trace on 1, I also get a value of 2 for my min. And you can see at x equals 0 we've got that vertical asymptote, so there is no critical value there, there's no extrema there.